I'm Kyota Shimada from Keio University. Today, I would like to present our research about dual measurement Pitot 2 prototype airflow and waterflow speed sensor for Seabird Biologging. The objective of this research is to develop dual measurement airflow and waterflow speed sensor for seabirds. And using this sensor, we can quantitatively measure the seabird flight and swimming speed. This will help us understand the movement mechanism of seabird movement. Previously, seabirds have attracted attention to their mobilities. They migrate over thousands of kilometers, and also swim underwater using their wings to catch fish. No artificial devices have developed with such excellent maneuverability, so it is important to understand their movement mechanism from both ecological and engineering perspective. To understand the natural movement of animals, there is a research method called biologging is performed. Biologging is a method where sensors are attached to the wild animals to record their behavior and environmental data. In this method, sensors have strict requirements. For example, sensors for seabird need to be waterproof and weigh less than 5% of bird's body's weight. Due to such strict requirement, only a limited amount of sensors, such IMU and GPS, have been used for seabird biologging so far. And by using these sensors, ground speed was calculated from GPS and IMU data, and seabird's movement ability was evaluated from ground speed data. However, ground speed is the sum of movement speed and external factor speed like wind and current. And additionally, relative speed to air or water is closely related to the movement mechanism of using wings. So ground speed alone is not sufficient to evaluate seabird's movement ability. In biologging field, these sensors have been developed to measure animals' movement speed. Waterflow sensors have been developed mainly for large animals like turtles and whales. These sensors are too heavy to attach the seabird. And in airflow sensors, there are very few sensors that meet the requirement. So in our previous research, we developed airflow sensor that could measure seabird airspeed. However, seabird's movement is particularly interesting because they not only fly but also swim. So to measure both his movement, we have been working on develop dual measurement airflow and waterflow sensor. I will start explaining previous Pitot 2 because our proposed sensor is based on the previous research. Previous sensor was based on the Pitot 2 principle. Pitot 2 measure the differential pressure with very simple and lightweight structures, and it doesn't emit anything potentially harmful to animals like heat or ultrasonic waves. So we decided to use the Pitot 2 principle. And as for waterproofing, we use a micro mesh filter to the dynamic and static inlet of the Pitot 2. This micro mesh filter is air permeable and waterproof, so it prevents damage to the internal DP sensor from water. So the sensor met the requirement for weight and water resistance. So from above, this sensor was suitable for, for airflow for seabird biologging. By improving this sensor, we developed a dual measurement sensor. This is our proposed dual measurement sensor design. To achieve the water flow measurement, we focused on the deformable characteristic of the waterproof membrane. As the sensor moves through the water, the membrane deforms under water flow pressure. The membrane deformation transmit the pressure to internal DP sensor, which enable the water flow detection. I will explain the measurement principle. The proposed sensor is based on the Pitot tube. So following the Bernoulli equation, the speed is calculated from the pressure data. For airflow measurement, DP sensor measure the dynamic pressure of airflow, which that's through the waterproof membrane. So the measured pressure equals the dynamic pressure of airflow. For water flow measurement, DP sensor measure the pressure changes caused by the waterproof membrane deformation. So the measured pressure is internal chamber air compressive pressure, so which is smaller than the dynamic pressure of airflow. As a result, the sensitivity is different for airflow and water flow measurement. Now I will summarize the sensor's requirement. These sensors are based on the characteristic of the target seabird. These requirements are based on the characteristic of target seabird. The sensor need to be compact and lightweight, and also need to measure different pressure ranges for airflow and water flow. By using the sensitivity difference explained previous slide, the sensor could measure both using a single differential pressure sensor. To meet the requirement, we developed and fabricated the sensor using the design mentioned before. This is a fabrication process. The process is simple. First, DP sensor are attached to the circuit board using wire bonding, and then assembled with 3D printed housing, and then the parts are adhered with epoxy resin, and finally, waterproof membrane were applied to the dynamic and static inlets of the Pitot tube to complete the sensor. Here is a photograph of the fabricated sensor. The sensor was compact and lightweight, specifically 25 millimeters and weight 12 grams. This sensor met this fabricated sensor met the requirement for weight and length. Next, we evaluated the pressure response of the fabricated sensor in air and water. Using a pressure calibrator, we apply the pressure to the sensor. For water flow measurement, we use the water-filled chamber. We also use the water-filled chamber. These graphs show the relationship between applied pressure and measured pressure. For airflow measurement, the sensor show the linear response, and the waterproof membrane have minimal impact on sensitivity. And for water measurement, we confirm the pressure reduction of measured pressure. Then we evaluate the sensor response to airflow. Using a wind tunnel, we applied airflow to the sensor. The graph shows the relationship between airflow speed and measured pressure. The relationship was quadratic, following to the Bernoulli equation. So as expected, the sensor detects the airflow speed with high sensitivity. Next, we measure we evaluate the sensor response to the water flow. Using a circulating water tunnel, we apply the water flow to the sensor. This graph shows the relationship between water flow speed and measured pressure. As the water flow speed increased, the measured pressure also increased. So we confirmed that the sensor measured the dampening dynamic pressure of water flow depending on the water flow speed. From these results, we confirmed that the sensor could measure both airflow and water flow based on principles. Finally, we performed a dummy attachment test experiment. The sensor dummy was attached to the Seabird with using tester tape for 1 day, and then retrieved. When retrieved, we confirmed that the bird was uninjured and dummy was not broken. So we are planning to conduct actual measurement experiments next summer. Please look forward to future results. Here's the conclusion. Thank you.